Okay, this is Chapter 2, Linear and Exponential Model. So just to quickly review, a linear model has a constant slope, and an exponential model is going to grow at a very fast rate. So that would be an increasing exponential growth model. You also have decay models. So we will talk about all of these in this chapter. So here's just some quick examples, and let's go on to the next slide. Okay, we talked a great deal about linear models in Chapter 1, but this is just another little reminder. So you can represent slope a couple of ways. You want to understand that it's a constant rate of change, and you also want to understand that you can use this delta symbol, change in y over change in x, and the delta is kind of a chemistry type symbol that is a change. That change is y2 minus y1 in the numerator, and it is x2 minus x1 in the denominator. All right, so this would be the mathematical language used to represent slope. So in any linear function, the change in the dependent variable, so that generally is our y, but remember we also talk about it as our f of x when using function notation. And that change in the dependent variable is proportional, so they change at the same rate to the change in the independent variable. So usually that is x. It can also be time or anything else that you want to identify as your independent variable. So in this graph above, this I have y's and x's, so this is going to be your y, that's going to be your x. Here is a linear function. We can see you kind of build a triangle. The triangle helps us determine the slope. We can get the slope using this equation, and you can get the length of this distance from here to here using Pythagorean theorem. Okay, so that's the whole introduction to the linear models. So let's go on to the next slide. Okay, here we talk about the Fahrenheit lab, and we established this relationship, right here. Let me just change my color so it's a little bit darker. So here is the relationship we established. In this situation, the Fahrenheit degree measurement is the dependent variable, and the Celsius degree measurement is the independent variable. And this linear function will help us convert temperature measured in degrees Celsius into temperature measured in degrees Fahrenheit. Okay, the value of delta F over delta C is a constant, and we're representing that constant as the fraction 9.5. What's the measure and what are the units? So that's an interesting question. So let's also remember that we interpreted it as a decimal. I believe it was 1.8. Okay, just to remember what we had done before. Okay, so what are the units? Because you don't really think of units when you think about slope. So the 9 must be degrees Fahrenheit. That pertains to that. And the 5 is degrees Celsius. So what happens is this. If you want your F to be clearly in degrees Fahrenheit, we'll write it like that, then to get that, so here's your dimensional analysis piece of it, you have 9 over 5 times your Celsius degrees plus a constant of 32. Okay, so which you're going to add as degrees. In order to say that we can make that conversion, this must have Fahrenheit over Celsius so that the Celsiuses can cancel out, and you're left with a Fahrenheit measurement, and this 32 is degrees. All right, so that's good to understand because that's a little snippet into the world of dimensional analysis, And you really don't even think about that when you're using the equation for Fahrenheit. You don't think that you're converting in a dimensional analysis fashion. So let's move on to the next slide. Okay, here's a little word problem that's going to help us work with slope and have a better understanding of it. So it says that price, which is a function of time, this equation models the average price in dollars paid for a collectible toy T years after the toy is first marketed. Okay, then we see a series of questions that we need to answer. What is the average price when the toy goes on the market? Okay, so that's an average value. We'll talk about that in a second. How much does its price increase from one year to the next? If delta T is 2, what is change in price? And complete the table and identify the pattern of change. So let's try to complete the table. If you plug in a 0 for time, you get price. So when you have the initial price, your time is 0, that price is $10, and that is your initial price. Okay, so then you're going to plug in a 2. So 2 times 1.5 is 3, and 3 plus the 10 gives me 13. Plugging in the 4, you have a 16. Plugging in a 6, you get a 19. Plugging in an 8, you get a 22. And plugging in a 10, you get a 25. Now, you could have just put this equation in your y1, and then if you made your delta t, and they're going to say it's delta x, but we're treating it with time as a variable, your delta t, when you said table set, would be 2, and your starting point is 0, you would then generate this table right here. So you should go back and check to make sure that you know how to generate this table. So what is the average price when the toy goes on the market? So let's think about that. How would you figure out the average? Well, if you only had these 10 years, you could average these numbers and get your average price. So let's think about this for a second. It models the average price. Okay, so let me take that back. What is the average price when the toy goes in the market? When does it go in the market? It goes in the market at time 0. Okay, so that price is $10 because the prices that we're working with are the average prices. We do not need to take an average figure. How much does its price increase from one year to the next? So it looks to me, because I see it's modeled as a linear equation, the price increases by $3 each year. Okay, so each of these goes up by $3, which is a constant rate of change, which is what we'd expect. So therefore, I can figure out what's my slope now. So let me think about this for a second. Hold on. Okay, so how much does it increase from year to year? Is the quick answer 3? No. The quick answer is not 3, because if I just looked at the table, I see that my years are changing by 2s, so I have temporarily misled you. Every year, the price goes up by the slope value, which is 1.5, okay? Every 2 years, which is how our table represents it, the price goes up by $3, which makes sense. So it says if the delta t is 2, so if the change in time is 2, which is what it is here, what's the change in price? Well, that is 3. Because what's the delta t in B? The delta t here, the delta t, has to be 1. Okay, so we've completed the table, and we've identified the change as a linear change, okay, because both the t goes up by 2 each time, and the price goes up by 3 each time. It's a constant rate of change that makes the slope 3 over 2, which is indeed represented right here as the 1.5. All right, so you can think of this many ways, and you can practice using your graphing calculator also to make sure you understand where this table comes from. And then you need to be able to answer these questions so that you're making sure that you're looking at what values they're giving you. Don't assume you're reading directly from the table at any one time. Okay, let's go on to the next slide, which will be a special case analysis. Okay, so these are two special cases of lines. So I'm going to use my red color to talk about this horizontal line right here. So remembering that I'm going to label this as a y and an x, remembering that slope is change in y over change in x, I picked 2 points. Here's a point, here's a point. What's the slope of that line between those 2 points? All right, so what do you see? Because this is going to help you always get this question right. What I see is that I have a certain change in what? So do you have a change in y? Let's start with that. I do not have a change in y. That change is 0 because the y is 5 in both cases. So I got the 0 by saying 5 minus 5. Then look at your delta x. I have 6 minus 4, which is 2. This is 6 minus 4. That's how I got 2. Here is my slope. 0 over anything is 0. Okay, so that 0 over 2 is 0. So this slope of the horizontal line is 0. Let's change to green, and we'll talk about the vertical line. Okay, the vertical line abides by the exact same slope equation, change in y over change in x. We'll do the same thing, and we'll pick 2 points here and here, and let's fill in this equation. Okay, change in y. The y changes, so I have 2 minus 1, so that equals 1 in the numerator. Okay, so it looks like we're in business so far. Now the x. Oh, wait a second. The x is 3 both places. That change is 0. You can never divide by 0. So what happens is this is undefined. So your slope of a vertical line is undefined because when you try to do the equation, you force yourself to divide by 0. But in the other case, the case of the horizontal line, that slope equals 0. So don't get these two confused. And if you do get them confused, or if your students get them confused, do this analysis where you actually pick points and solve for it so that you don't have to necessarily memorize the fact that your slope is 0. Okay? So that's the special case, and let's go through some quick questions on the next slide. Okay, so here's some quick questions about lines. So does a horizontal line, so it looks like this, here's a horizontal line, does this horizontal line represent a function? Well, I would say yes. How come? Because it passes what test? The vertical line test. Okay, if you draw a vertical line anywhere on this function, it will only cross it in one place. If it crosses in one place only, the relationship between the points that create the line is a function. What about a vertical line itself? There's a vertical line. So here's my axes. Here's the vertical line. What do you think about a vertical line test? It's going to completely cover the vertical line. If it completely covers the vertical line, it intersects the vertical line in an infinite number of points. So therefore, it is not a function. So you can say no, because it fails the vertical line test, which allows for only one intersection. So therefore, it is not a function. What is the equation? So let's think of this, of a vertical line through the point 4, 6. So if you had the point 4, 6, let's see where I am. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So you want a vertical line, vertical line through that point. So it's going to look like this, that. So what will that equation of a line be? Well, does it have a y value? It has lots of y values, but it's a vertical line, so its equation would be x equals the 4. Okay, because x is always 4 no matter what you do, and the 6 is infinitely changing. So x equals 4 is that line. Okay, what about this? If I have a horizontal line that's going through the point 1, 2, 1, 2, 3, if it's horizontal, it's going through that point right there. And what do I say about that? That's a y equals line. So y equals, what is the y-intercept? It is 3. What is the slope? Let me back up. What is the slope? The slope of a horizontal line is 0 times x. So you can write it like that if you would like to, but this is acceptable also. This form, the nice thing about this form is that it demonstrates that you have an understanding and a knowledge of the slope of a horizontal line. Okay, but here is all that is required. So understand these concepts because these are where your students will get tripped up, so make sure that you are confident with it. Okay, so we're now moving into exponential models. So I have a table, just like I had a table before that we filled in for the linear model, but look at this table. So examine this table. Is this function linear? So for it to be linear, the change in each of these variables has to be constant. Okay, so let's look. This change is 1. That's 1. That's 1. That's 1. That's 1. So on the left, everything changes by 1. So as time goes on, so time is the independent variable. Look what's happening to the number of bacteria. So this goes up. So this is increasing by 1, but now it increases by 2, now by 4, now by 8, now by 16, and now by 32. Okay, this is your classic exponential growth. So the kind of function this is an exponential function. Now, we have some options. We can put this in our L1 and L2. So this would be your L1 and your L2. And you can get a formula for this. But if you look at it, you can kind of figure it out. So this is what I would write for my exact formula. The bacteria at that time, so elapsed time in 20-minute intervals. So 0 is your starting point. So 0 is your k value. We'll talk about the parts of the exponential function in just a second. What's your base? What base is being represented here? Well, it looks to me like it's base 2. Okay? So 1 times 2, and then you raise that to the power, the exponent, thus an exponential equation. So I want you to stop and see if you can put this in your graphing calculator and get the same model. So if you run this as an exponential regression, so to do that, put the first column in L1, the second column in L2, and then when you go down to stat, you have to go down to the next page to number 10, and that's your exponential. And if you run it, what you're going to see is it's going to tell you that y equals a times b to the x, and it will tell you that a is 1, that b is 2, and you have to know that this x is the t because that's our variable. And it's also going to tell you that I have picked a perfectly exponential function. Okay? So that's what you get from running it. So get a handle on this. What I'm seeing in terms of the terminology, this is the base, it's base 2, this is the power. The fact that your variable is in the exponent makes it an exponential function. Okay, and it is indeed a function. So if you graph that, just using the data, you're going to see that your graph looks like this. Okay, so here you're going to have your time, and the growth of your bacterial function is on your y-axis. Okay, so that's what it looks like. So clearly the piece back here, which will show up in a graph, doesn't have a meaning because we don't have negative time. So we want our function to be in the first quadrant and include the y-intercept right here, which is our starting point. Okay, so let's go on to the next page. Okay, so here they give us a general form, and they ask us to analyze the parts of this. So here's your dependent part, okay, and this is your constant. Your constant can also be your starting value, okay. Population equations, it would be your starting population. Okay, here is your base or your multiplier, also called a multiplier. Okay, and here is your independent variable, or you can call it your exponent. Okay, so identify the parts. Okay, now if decay is happening and not growth, how would this equation change? Excellent question. Okay, so if b is greater than 1, you have a growth situation. Okay, if b is less than 1 but greater than 0, you have a decay situation. Okay, what if b is 1? Then you have a constant situation. Okay, so that's how this works. Okay, this link right here is a worksheet by CUDA software, and it has to do with exponential growth and decay. So I'm going to post this for you. So I'm going to post it along with the answers for it. Okay, so you can look for that. You can also just search for it yourself with this internet words. But I'll post it and the answer on this day. So wherever you get this posting, I'd like you to do these problems. There are 6 of them. And on the second page of the document, I give you the answers. Now, a couple of them are going to be a stretch problem because they have just very complicated answers. But look at the answers and see how close you can get to them. Okay, so in this next slide, we're going to investigate a step function. And it's kind of like, it's also called a piecewise constant function. So I'm going to post this for you, and this document gives you a whole bunch more information about step functions. Okay, I just want to touch on them because they're kind of interesting, and they happen a lot in real life. So I'm going to take a little time to do this graph. So the shoe size is the dependent, okay, so that's the y. and the foot length is the x. So notice that you have an inequality statement for your foot length in every single case. So how would you handle that? That is the question. Okay, with the miracles of internet, I have filled this whole thing in for us. So a little commentary on this. So here is the shoe size model. Okay, so in reality, you don't have a continuous function for shoe sizes. So it's really going to be a model like this, where it cuts off at various places, and that puts you to the next size. Because you cannot generally order an 8 1/4 size shoe. Usually it's just an 8 and an 8 1/2. Sometimes you don't even have the option of having the half sizes. Okay, it depends on the shoe type and model and company. So shoe sizes are not continuous. They really are piecewise. So let's talk about this. A couple of things. Over here at the bottom, like right here, I put this little like lightning type bolt, and that's because my graph does not go up from 0 on up. It actually jumps to start at 5 on the y-axis and to start at 8 1/2 on the x-axis. So you have to put a break on your line so that it is obvious what you're doing. You need to have uniform increments. So I can clearly, on the vertical axis, you see that I go up by ones once I actually start. So the y-axis is the shoe size, and the x-axis is your foot length. All right, so look at the x-axis. This foot length, is it going up uniformly? It appears not to be, because I have 8 1/2, and I have 8 2/3, 8 5/6. So let's think about this. Isn't 8 1/2 really 8 3/6? Isn't 8 4 2/3 8 4/6, and then 8 5/6? Isn't 9 really 8 6/6? So looking at the x-axis, I can see that I'm really going up by 1/6. So let's just quickly look at the shoe size, size 5. Okay, so it says the foot length. You are going to get a size 5 if your foot length is less than or equal to 8 2/3. So that's how I got this first filled in dot. Okay, or greater than 8 1/2. It cannot equal 8 1/2. It has to be greater than, therefore I have an open circle. All right, so I'd like you just to look at this. Print out this document. It gives you, as I said, more than you ever want to know about these kind of functions, but they're kind of fun to work with, and it really is a nice way to introduce inequalities to your students. Just a small little glimmer into it. I wouldn't go to town with it, because you're just going to probably confuse them, but you can pick up some good pointers, and they can pick up some good understandings on how functions work with a function like this. Okay, so in this slide, I'm doing a very poor job of trying to get this little tiny graph on this grid. But I want to give you an idea about a piecewise function, and then I'm going to erase this and show you a more typical one in just a second. Okay, so piecewise linear function, each of the pieces are lines. So here is your first piece. So this first piece is this little tiny blue line here. I'm going to change my colors. This next piece, which is this piece, goes from t is less than or equal to 6 and t is greater than 1. So why don't I do this? I'm going to erase some of this up to here. And now why don't I start about here? This piece is very tiny, so it's hard to see. I have to start with an open circle because t is greater than 1. I'm going to go up to 6, and at 6, I'm going to have a closed circle, and that is the that is the bike portion. So this is the bike portion in pink. Okay, so then we'll change again. Why don't I change to blue? Well, let's not do blue. Let's change to purple for this last piece of the triathlon. And that last piece is always going to be the run part. And let me erase that here. So the run ends at the end of the bike. So it's going to be an open circle there. And then it's going to go to about here. This will be a closed circle, and that's another piece of the line. So here is the run. Okay, so you have the first piece, the first little blue piece that's very difficult to see. Right in here would be the swim. All right, so what I want to do now, oh, and by the way, this problem was on page 78, and it was number 1 in your textbook. That's worth looking at. Okay, let's do another piecewise function on the grid that's going to make it easier to see. Okay, so I'm going to use that on the next grid. So let's not do the traditional problem I wanted to do. I'm going to change it up and do something different on the next grid on the next slide. Okay, so I am going to do this problem because it does do a little decay piece. So let's talk about that. I'm also going to do a worksheet on piecewise functions. So I will post that for you as well under this, and you'll have that to do and get a chance to practice piecewise functions, and I'll post the answer key as well. So let's look at this, and again, we're going to have a hard time kind of doing this. These are going to go up by 1, so I'm going to say 1, 3, 5, 7, and 9. So let's just go up to 9 because that's all I can really see on my grid right here. This is going to be time down here. Okay, this is going to be money up here. Okay, here's your formula above, and here the domain restrictions. Okay, so this is an exponential function. I see that because I have a base of 0.8. It is a decay because that base is less than 1 and greater than 0. Here is your exponent, making it an exponential function. This is your starting point. So I believe what I did, I said, I'm not doing this really justice, but you get a sense of it. This is where the 3,000 is at time 0. That is your starting point. Because you're doing a decay down to 8.5, you decay. So it says until time is less than or equal to 8.5. So just to give you a rough sketch, this is where 8.5 is, right about there, at the end of that. And it says it's going to be less than or equal to it. So that means, let's just say we get down, oh, I don't know, about here, just for argument's sake. And that's a decay, so it's going to go quickly down, okay? It's not a line, it's a linear, it's an exponential function, not a linear function. Okay, so then we have a linear function with a negative slope, a slope of 300. That's going to start right where this one left off. Okay, at the same time, we're going to put an open circle, and that is going to dive in a linear fashion. Okay, and it's going to stop where t is less than or equal to 10. So I have an arrowhead, but know that the arrowhead is going to stop at 10. So that gives you a sense of the piecewise. But let's go ahead, and I'm going to do a rough sketch of a piecewise function so that you understand how they work. We'll do that on the next slide. Okay, so let's just talk about this piecewise function without having formulas. So what's happening here is, let's say I have a cup of water. It's kind of cool water, 60 degrees, so kind of, lukewarm. And it is sitting on the table from time 0 to time 3. At time 3, and that temperature is holding constant. At time 3, something happens to drop the temperature. So let's just say I add some colder water to it, and it immediately drops the temperature. And then the temperature continues to drop just a little bit up to time 5. At time 5, I put in a handful of ice. That will drop the temperature right away, and that temperature will continue until I pour out the glass at time 7. So you can see you have these gaps. That's your classic piecewise function. So I have a worksheet I'm going to post. I want you to do this worksheet. I will also post the answer key to it, so you have that to check. Okay, so this ends the video for chapter 2, but check, there are more activities posted online for day 2.